Hello class, welcome to Geometry Lesson 10.3, which is all about chords. By the end of this lesson, you should be able to relate the length of a chord to its central angle and the arc it intercepts. So let's quickly refresh your memory on what a chord is. So we've talked about, okay, here's the center of a circle, here's the radius. If we go all the way across, it's a diameter. But if I draw something that does not go through the center of the circle, that is called a chord, okay? So that's just your quick little refresher on chord. It cannot go through the center of the center. Or actually, I should say it can, but if it goes through the center of the circle, we have a more specific name for it, and that's diameter. So a diameter is a type of chord, but a chord does not have to go through the center of a circle. Okay, so a chord is a segment whose endpoints are on a circle. I kind of just talked about that. But what if I ask you, why can I say that segment RS is congruent to segment UT? So if we look at this picture here, I want to prove that those two segments are congruent. I'm not going to write a formal proof. I'm just going to kind of talk through it. If we start with, actually, this bubble right up here, I say that it says angle RQS is congruent to angle UQT. So RQS is congruent to UQT because they are vertical angles. Now, while that is true, I want to warn you to always be careful to make sure that you actually have vertical angles. In a circle, the way that you can tell if you have a vertical angle is, you see how we have these two dash marks, the two congruent symbols? That shows us that those were cut in half and those are exactly equal. That means that that SU segment is actually a diameter. Sometimes they'll give you pictures that you don't actually have the diameter. Like you'll have a circle and then you'll have something like this. In that case, those are not vertical angles because in order for it to be a vertical angle, you would have to have something like that, okay? So in this case, we do have vertical angles because SU and RT are both diameters. Then, moving on, it tells us on the picture that all of those are congruent because they are all radii of the circle, and all radii are congruent. So if I look at this picture, I now have two triangles with a side angle side situation happening. So if I know that I have a side angle side situation, I can say triangle SQR is congruent to triangle, let's see, that would be TQU. And if I know that those are congruent, it's because side angle side. And if those are congruent, any part of them is also congruent. So I can say segment RS is congruent to segment UT because of CPCTC. So on the next question, I'm going to give you something like this. I want you to figure out which of the triangle theorems tells you that the triangles are congruent, because then no matter what, your next step is CPCTC. So on this question, why is angle BAC congruent to angle DAE? So tell me, is it side angle side, side side side, angle angle side? Like what is happening to tell us that those two angles are congruent? Good luck. All right, for this problem, hopefully you realized that, okay, they gave us two congruent sides. They said segment CB is congruent to segment DE. And then the rest of those lines are all radii, and all radii are congruent. Therefore, I have two triangles that are congruent by side, side, side. So then corresponding parts of congruent triangles are congruent, or CPCTC tells us that angle BAC is congruent to angle DAE. So on your homework, it'll ask you, not necessarily for the CPCTC part, but it'll more likely ask you, how do you know that the two triangles are congruent? Okay, so this lesson, There's going to be a lot of slides of just theorems and not a ton of actual examples. You need to memorize the information in these theorems. Now, I'm not saying that you have to memorize the exact wording. Like, if two chords in a circle or in congruent circles are congruent, then their central angles are congruent. No, I'm not expecting you to ever spit that out back at me. What I do need you to know is if I give you a circle and I tell you that MN is congruent to PQ, if you know that information, this theorem is telling you that these two angles are congruent, and vice versa. If I tell you that these two angles are congruent, then you can tell me that these two segments are congruent. That is what I need you to remember, okay? So if you have the outer segments, the two chords, and you know they're congruent, you also know that the angle making those two things are congruent, and vice versa, okay? If you have questions on that, please be sure to ask. Theorem 10.4. Again, I'm not asking you to memorize all of these words, but you need to know the information. So, what if we don't have the triangles anymore? I just have these two. I'm actually going to erase the chord there. What if I have these two arcs? If I know that these two arcs are congruent, then I can say that the two chords made by those arcs are also congruent. And the other way around. If I know that the two chords are congruent, then I can say that the two arcs are congruent. So that's the theorem and its converse. Theorem 10.5. Again, please don't try to memorize it word for word. Just you need to know the information. So if I know that SE is congruent to SF, so those two things are congruent, then I also know that AB is congruent to DC, okay? Something key to notice there too is also those right angles. We'll talk about those more in just a minute. But if you know that SE is congruent to SF, then you know that those two chords that they're touching are also congruent, and vice versa. If you know that AB is congruent to CD, you also know that SE is congruent to SF. Okay, so I'd say that one's probably the trickiest so far of what we've looked at. All right, theorem 10.6. This is where we start to get into slightly tougher things. This ends up getting used way more in the real world examples in your homework assignment, okay? So theorem 10.6, if we have a diameter, okay, in this case it's CD, and that diameter is perpendicular to a chord, so in this case that chord is AB, so if we have a diameter that is perpendicular to our chord, then we know that chord is bisected. So I know AE would be congruent to BE. And the other way around. If I give you a picture and I tell you that AE is congruent to BE, then I can say that it is also perpendicular. And like I said, this is what you're going to use to solve a bunch of real-world problems. You'll end up doing some Pythagorean theorem. You'll connect, and then you'll see, okay, I have a right triangle. I can solve for any of these sides. Remember, this side would be a radius. So a lot of people tend to forget what to write down for that side. So always look for which side in the triangle makes a radius when you draw your picture. And if you're feeling confused and overwhelmed by all of these theorems, that's okay. I will help you through it, okay? All right, theorem 10.7. If we have a circle where we know that a chord is cut in half and it meets the other line at a 90-degree angle, we know that the line that cuts through is actually a diameter, and it's going to contain the center of the circle. All right, now let's try another problem. and we're going to combine kind of all of those theorems into one, okay? So we have a tunnel, and an engineer is designing a service tunnel to accommodate 2 trucks simultaneously. So the tunnel has to be able to fit 2 trucks at the same time. If the tunnel can accommodate a width of 18 feet, what is the greatest truck height that the tunnel can accommodate? So I don't know if you guys have ever noticed if you drive into a bridge or under a bridge, or if you drive into a tunnel or under a bridge, there's usually signs saying trucks no taller than this height. That's because if trucks that are taller than that height try to go under, they're going to end up hitting the bottom of the bridge or the edges of the tunnel. So this is actually a really important thing for engineers to consider as they design tunnels and bridges, because if they design something and they don't measure it properly, it could be taken out by like a semi or something. Okay, so we've read most of it, but then they also need to tell us to subtract half of a foot to account for fluctuations in pavement. I think you guys are pretty familiar with fluctuations in pavement since we are in Minnesota, and all of the temperature changes causes the road to change, and we end up with all of those potholes, right? So you guys are used to all of the fluctuations in pavement just because of our temperature differences. So, all right, let's start by taking the information in that picture. Maybe let's try drawing a slightly simpler picture. So I'll do my best to draw a circle. I feel like that wasn't great, but not horrible. And the information that we have, if we think about this, okay, I need the top of those trucks. Okay, so that's 18 feet. So that's going to be a chord, right? That's not going through the center. So that's going to be 18 feet across. And then the radius or the diameter of the entire circle would be 27. So a radius would be 13.5, because remember, a radius is half of a diameter. Okay, and then let's just draw that diameter. So we're going to say that this is the center of our circle. And I'm going to connect from C to the outside of the circle is a radius. So I know that this is 13.5. And if I drew that chord through the center, like I said, that made it a diameter. But remember, that also cuts that chord in half. So if the whole thing's 18, half of it is 9. And then this side, we don't know what that measure is. Okay, so now I have a nice little right triangle, right? So if I just take that part to simplify it maybe even a little bit more, we have 13.5 here, 9 here, and x here. So my hypotenuse is 13.5, so I'm going to put that number by itself, use some Pythagorean theorem. So I'm going to say x squared plus 9 squared equals 13.5 squared. And if I solve that, I can subtract the 9 squared over. So 13.5 squared minus 9 squared, and then take the square root of that whole thing. And remember, on your calculator, you can actually type it in just like that. You can hit second x squared to get that square root. 13.5, you can use the squared key. Minus 9, again, use the squared key. And you end up with x is approximately 10.06. So we know that this right here is approximately 10.06 feet. And then remember, we have to also add the distance from the ground to the center. So if we think about that, we had right here, the picture's a little tough to see, but they were showing us that from the ground, like down to complete the circle, that's 6 feet. So we actually have to subtract that from the amount that we have looked at. So, or sorry, not the amount we've looked at. This whole thing, the blue line would be 27. This would be 13.5. We have to do 13.5 minus that 6 feet. That would be kind of underground, right? Because our roads shouldn't look like that, right? We can't easily drive on that. If we drove on the angled something like that instead of a flat road, our vehicles would end up going into each other. So 13.5 minus 6 tells me that there are 7.5 feet from the center of the tunnel down to the ground. So we know that distance. And then we have to add the distance that we just found, which was 10.06. So we have 10.06 plus 7.5 equals 17.56. But then remember the last bit of information. We have to account for any fluctuations in the pavement. So we're going to subtract half a foot. So 17.056 minus 0.5 leaves us with 17.06 feet. I don't know why the pen keeps changing color, but that means that the greatest truck height the tunnel can accommodate is 17.06 feet. And when we see those signs for trucks as you approach a bridge or a tunnel, you never see like the decimal. We normally just see like max height 17 feet. They usually just round. I'm going to just quickly talk through this again because there's not a lot of examples in this video, and you are going to do things kind of like this, okay? So let's talk through the process one more time. We started with the picture and all the information. I drew a simpler circle, and I took my diameter, cut it in half because we rarely use diameters. We're going to use the radius a lot. So once I drew my picture, I pulled out that little triangle so that way it was a little easier to work with and see. You guys are more familiar with seeing just a triangle like that. I did my Pythagorean theorem and I solved for that distance. Okay, so then I labeled that distance on my picture. And then I looked back at what I was given and realized that, okay, tunnels have a flat bottom and that this was 6 feet. So if I did the 13.5, because that's my radius, minus 6, I was left with 7.5 from the road to the center of the tunnel. So I could add these two distances because that's how tall the trucks could be. And that's where I got the 17.56. And then I subtracted the half foot in order to account for the fluctuations in the pavement. And so that gave me 17.06 feet for a maximum height. Okay, and our last slide is our concept summary. So hopefully you took pictures of all of the theorems. If not, I would recommend maybe going back and taking another look at those and making sure you know the information in there. But here is a nice little summary of most of the stuff from the video again. If you have any questions at all, please do not hesitate to reach out and ask questions. I am more than happy to help you. Have a great day.